I am going to, as I said, didn't just allude to, but downright said in class, start off with talking about how Maxwell's equations predict electromagnetic waves and the speed thereof, and then I'll go to review stuff for the exam. So, starting right off, Maxwell's equations. The four equations, both the integral form and the differential form. Now, in this case, I was a little less specific than I was with the equations I showed in class yesterday, because I put, equals 0 for Gauss's law of magnetism, and I believe I put something in there that had to do with the magnetic density yesterday. I may not have, but of course, what is the magnetic charge density? It's always 0 as far as we know, because magnetic monopoles don't exist. They're always in dipoles, so it's 0. So we have these equations, and James Clerk Maxwell realized that if I combine these equations, they will predict a wave. Now, to predict a wave, you have to have something that has the wave equation. That is, it has the form of oh, forgot the seconds. So I will put just f for function here. And then in parentheses, I have 1 over the speed squared. This is what we call the wave equation. And if, nice use of parentheses, quotation, the wave equation. If a function fits into this equation, that is, if I take the second derivative of the function with respect to position, and that's equal to 1 over speed, well, that's equal to a constant times second derivative with respect to time, then that is a wave. It can support a wave. And you can get the speed by whatever's in that parenthesis. And so Clerk Maxwell realized that we have this relation. So what is it that's going to be in the position of that function? Turns out it could be either electric field or magnetic field. So we're going to go through and we're going to put these Maxwell's equations together to show that it falls into that form. And we're going to do it, we're going to start with, here's the way we're going to do it. Take the curl, that is del cross of both sides of the differential equation for Faraday's law. And then we're going to use an identity. So this here is an identity. And then we'll do substitution of the differential equation for Gauss's law into that, and a substitution for the differential equation of Ampere's law. So we're going to use 3 of the 4 Maxwell's equations. We're going to use Faraday's law, Gauss's law, and Ampere's law, plus an identity. So let us get started. So what is Faraday's law of induction? Just go back here. Faraday's law, del cross E is minus dB dt. Looks a little different than what we did before because we did the integral form. So del cross E is a minus dB dt. So there we start. And what did I do with this equation? According to our instructions, take the curl of each one. So I'm going to add to this. Apparently I can't make a triangle. Del cross so there I took the curl of each side. Now the left side is del cross E. And so then we're going to take, I don't want any of those colors. I want this color. Then I'm going to take this definition that's in the box and replace the left side with del of del dot E minus del dot del of E. Oh, I've got a vector sign. Equals. Now, minus sign, of course, I can move that out of my, move that across the del without a problem. The derivative is it's a partial derivative with respect to time. So since the del is a spatial operator, it's partial derivative with respect to space, and t is a partial derivative with respect to time, the two don't affect each other. So I can move the derivative, the d dt, outside of the del as well. So I can rewrite this as minus d dt of del cross B. Right, so I move the minus d dt past the del cross because the d dt and the del operators don't interact. Partial with respect to space versus partial with respect to time. And now I have two substitutions. So I will go back to, I will do this substitution in red, substitute the differential form of Gauss's law for a vacuum into this. Oh, actually, I should do some other things before I do that. No, I start with that. Substitute the differential form of Gauss's law for a vacuum. So Gauss's law is del dot E is rho over epsilon 0. So we had right here del dot E, so that's rho over epsilon 0. But with the understanding that if I'm doing this in a vacuum, rho is 0. So 0, because the rho is 0. Minus, now del dot del. Del dot del, we usually write it, it's a vector if it's del dot del, right? Or if it's del with a vector sign, it's a vector. But when you do a dot product, that makes it a scalar. And so this is actually a scalar del squared of the electric field. So there I've taken care of the left-hand side. I'll change to blue for the right-hand side. Substitute Ampere's law for the del cross B. So del cross B is this whole thing here. Come on. And I have to go back to remember what the last part was. Yeah, it was just mu naught J. Where that J vector is the current density. And if I'm in vacuum, it says, remember that if you're in vacuum, that J is 0. So now I have an equation. Notice I have a minus on both sides. I'll multiply by minus 1. I think we can all accept that. And so I have del squared E is equal to mu naught epsilon naught d second E dt squared. Now, when you look at that, you probably recognize that's not identical to what I said we had to fit. How is it not identical?
It's not.
Yeah, instead of one, well, no, that part's the same. The left-handmost part, I said the second derivative with respect to x. Well, del squared is just the three-dimensional equivalent to that. And so del squared is just a more generalized form. What I gave you was a one-dimensional version. If you go to 3 dimensions, you replace this here with, d second dx squared f plus d second dy squared f plus d second d z squared f. That's what we have when we have the del squared. And so it's just the three-dimensional form. So it is now the wave equation. And then we'll look at what I think it was Carrie said. The wave equation said that this thing right here needs to be 1 over the speed squared. And so we can take this and say, if this supports an electromagnetic wave, then the electromagnetic wave has to have a speed of v is equal to 1 over the square root of mu naught times epsilon naught. And without taking the time, if you go through and you put in the values for mu naught and epsilon naught, you find that that gives you 2,997,92458 meters per second, the speed of light. And so, oh yeah, no, actually, I didn't say point, did I? I think I said 2,997,92458. And so Maxwell, of course, they didn't have the numbers as exact as what I just quoted. They hadn't defined the speed of light as exactly 2,997,92458 meters per second at that point. But he saw that that speed came to, within experimental variation, exactly what had been determined for the speed of light. And he said, wow, they must be the same thing, which I've said, not a really logical statement, but it turned out to be correct. So that's the math to show that electric and magnetic fields will support an electromagnetic wave. Now, I did it starting with Faraday's law, which was del cross E, or del dot E, excuse me, del cross E. I could have started with Ampere's law and gone and just done the same equivalent thing, and it still would have worked out. So you could get it in terms of E or in terms of B, and you'll get the same answer. So any questions on that derivation? Obviously, this is not going to be on today's test because it's a little quick to say, here, I told you this morning, make sure you've got it totally internalized by this afternoon. So just like transients weren't on the last test, this won't be on this test. Yes?
What is the significance of what we're writing here for the sake of clarity?
Okay, so the significance of this is that electric fields and magnetic fields, so electromagnetic fields combined together, can form a traveling wave. And it tells us that the speed of that traveling wave has to be this. Now, I did it only for in vacuum. If you're not in vacuum, like let's say you are in a material with, well, I can't think of any material, urethane. Urethane is a very common material used for insulators on wires. If you're in urethane, both of these numbers are different, which means the speed of the wave is going to be significantly different. But the derivation, I only did it for vacuum. If you did it in another material, it still works out. So the output is, or the outcome of this is electromagnetic waves can, or electromagnetic fields can support waves.
Okay.
Okay, any other questions before we go to reviewing for the exam? Aaron.
Is this just one of the ways that you can show that because you used like those orders of equations?
Yeah, it's one of the two fundamental ways.
Okay.
The other fundamental way would have been to start with this equation and take the curl. I'm sure there must be other ways as well, but you have to combine the equations.
But you did use all four in it?
Actually, I used 3 of the 4.
Okay.
I did not use, I think it was this one I didn't use.
Okay.
Not that there's anything wrong with that equation, I just didn't use it. Truthfully, it's all of our favorite one because it's 0. You don't get anything useful out of it other than I can always apply it and I always am immediately done. Okay, so let's go to the test. I thought that this was going to take 2 pages, so I put a blank page in. I worked efficiently. Okay, so these are the things, the calculus-based things that could be on the exam. You could have something that has to do with transient circuits, both RC and RL. RLs were introduced in this section. RC was introduced at the very end of the last section, hence wasn't on the last test as one of the options. Ampere's law, the Biot-Savart law, and Faraday's law of induction. Ampere's law and Biot-Savart law are the 2 laws that tell us that current produces a magnetic field. Just like last test when we had the 2 equations of Coulomb's law and Gauss's law that said electric charge makes an electric field. We could solve problems using either one, but we chose the one. What did I give you on the last test for the calculus problem?
Thin wire and a semi.
Right. Which you asked me about in the class, the review class before the test. Very astute of you to ask about the question that turned out to be on the test. So you had to make a decision there. Do I use Coulomb's law or do I use Gauss's law based on your symmetry? We have the same thing with current producing a magnetic field. You have to make the decision. Do I use Ampere's law or the Biot-Savart law based on symmetry? And the last one we have is Faraday's law of induction. That is that, well, using the equation. So let's look at each one of these individually. So starting in order, transient circuits. Transient circuit is a circuit that's changing from state A to state B. Now, I'm not going to give you a circuit as hard as the one I'm going to do for the demonstration today, but you will have either resistor and capacitor or resistor and inductor with the power supply and a switch if you have a transient circuit problem. And then you will be required to find, what is the equation for the current as a function of time, or what is the equation for the voltage as a function of time. So in that situation, you want to start by using your 3 rules that relate voltage and current through the different devices in your circuit.
Are you going to give those to us?
Yeah, they're on the equation sheet, aren't they? They should be.
I don't see them. Doesn't mean they're not on there.
I will double check, but I'm pretty sure they were on there. Okay, so once you have found the relationship between voltage and current through each device, then you're going to, depending on your circuit, did you find it?
No,
They're not. I'll have to, fortunately I haven't printed the test, so I can still stick them on, but I was sure they were there. Use Kirchhoff's voltage law if it's a loop, Kirchhoff's current law if it's parallel things. If you only have, well, you still have the option of, your if you have a circuit like this, we have things that are in parallel, except where's your switch going to be? Depending on your switch situation, well, there is no way to put a switch in here that's going to open and have all 3 of them there at the same time. It's going to switch it, so you're probably always going to have a loop. If you have something that has an inductor as well, then like this, you'd use Kirchhoff's current law for a node. If you have something that's a loop, which is what I'm going to do, because it's what I always do. So if you have something that's like, I'm going to put this for my if you have something like this, because it's a loop, then you would use Kirchhoff's voltage law. So I'm going to take this And this has all three, an R, an L, and a C. And I'm going to put my switch here so that when the switch closes, I have a loop. Before the switch is open, I have no current. And analyze this as you would on the test. So, first thing I need to do, according to my instructions, is to relate voltage and current through each one. So what's the relationship between voltage and current through a resistor? So V resistance is equal to IR. I didn't put I sub resistor because they all have the same current. What about through a capacitor? It's on the screen right now. Okay, and what about an inductor?
That's the L, the N.
Okay, so there I have my relationships between the three. Now I am going to make a Kirchhoff's voltage law. And so I'm going to go, if I start here, I'm going to go up the EMF minus the voltage through the resistor, minus the voltage through the capacitor, minus the voltage through the inductor is equal to 0. I'm going to substitute now where I can. Also, I'm going to put E equals, move it to the other side, so all the minus signs become pluses. So the voltage through the resistor was IR. Voltage through the capacitor. I don't actually have a voltage through the capacitor equation here, right? So I'm just going to put plus V capacitor. And then voltage through the inductor will be L di dt. Now, if you look at this, I can take the derivative of everything and then make a substitution for the voltage capacitor because I had voltage capacitor was in a derivative form here relating to current. Because I want to get one variable. Right now I have two, voltage capacitor and current. And so I'm going to take that equation and take the derivative. If I take the derivative of VC with respect to time, that's current over capacitance. Now I have a second order linear differential equation. I'm not going to give you something that has both an inductor and a capacitor. Hence, you're not going to have a second order differential equation. I have the second order because I had both the inductor and capacitor. So you would only have a first order in your work. Now, just a quick explanation of what we do here in differential equations. So the first thing we do is we solve this equation putting all of the I variables on one side and all of the non-I variable, the time, on the other side. But we have to keep the derivatives the way they are. I divide by the L, so I have, it's already done that, but I'm going to divide by the L, so I have the second derivative with no coefficient. So I'm going to have d second I dt squared plus R over L divided by the L di dt plus 1 over LC I is equal to 1 over L dE dt. That's the way that we typically write out. That's our standard form for writing this differential equation. And you have two solutions. The homogeneous and the particular. Now, who here has taken anything that's done anything like this? Two. So the homogeneous solution is the solution if right side equals 0. That is, you can have a solution that's equal to 0, plus you have the particular with the actual right side. Any constant multiplied by the solution you found for the homogeneous can be added to the particular solution without changing the outcome, right? Still going to be a correct equation. And so we do two solutions. Now here I am only going to focus on the homogeneous solution. I'm not going to go to the particular solution because, well, we've actually already looked at it when we did our AC circuits. That was the particular solution to this. And it requires a little more work. So I'm only going to look at the homogeneous solution. So for the homogeneous solution, we have that, and you learn this in differential equations. The solution to this has the form I is equal to A e to the bt. And so all we do now is we say, I've run out of page or space on this page. I did put another one. If I has this form, then if I take the derivative of I with respect to time, what does that give me? Got a question, Gabriel?
What is I, your shoulders in front of it?
And why does it have that form?
Why does it have that form? Because the best answer I have for you off the top of my head is when you have when you have derivatives of increasing order, the only solution that will fit is of this form. Why? That's not a clear answer of why.
So we just have to memorize it.
If you're taking differential equations, yes. And when we get to quantum mechanics, yes. Right now, you don't have to. So, and it comes from if you didn't have the higher one, if this one here was not there, and you separate variables, you would have, by separation of variables, integral would give you natural log, and then solving for I, you'd have I is equal to some constant e to an exponent. That's where it comes from as far as I know. But because we have another order, that's not a clear and complete explanation. So given this I here, the first derivative, bring down the b. So the first derivative is bi. Second derivative, bring down another b, it's b squared I. And so if I substitute those in, I'm going to have d second I dt squared plus r over L di dt plus 1 over LC, I equals 0, I equals a e to the bt. Substituting that in, I will have now an equation that says b squared I plus r over L bi plus I over LC equals 0. Factor out the i's. And this can only be true if the current is 0. We call that the trivial solution because I know that if there's nothing going on in the circuit, there's nothing going on in the circuit. That was a trivial discovery. Or the non-trivial solution that b squared plus r over lb plus 1 over lc has to equal 0. And so then you can use the quadratic to solve for b equals
This is not something we're going to have to do on the test.
That's correct. But I'm showing you the the complete solution if you had a transient RLC circuit. So now I would have B has two values here. Value 1 with the plus sign, value 2 with the minus sign. And so my total solution would be I is equal to A plus e to the B plus t plus A minus e to the B minus t. And that would be my solution. And the B plus, the B minus, those you match from the values of R, L, and C. And the A plus and A minus you match from your initial and final voltages or currents. So this was working out a larger problem than you will have. So what's going to be easier about your problem if this comes up on the test? You will be missing one of these, which means that when you make your equation, you're going to be missing one of these terms. You'll either be missing this term or missing that term. You're not going to be missing the R term. And so then you'll just have a first order differential equation instead of a second order differential equation. The first order differential equation you can solve directly, right? Because you separate variables. So make a choice. Which ones should we remove here, just for example? Okay, so example variation. No capacitor. Then I have this is my differential equation. For the homogeneous solution, I'm going to have I over D, did that backward, didn't I? Genius. When you separate variables, you need the D's on top. So di over I equals minus R over L dt. The left side has only I, the right side has only T. So then I integrate both sides independently, going from I initial to I at whatever time I'm looking, integrating from time initial equals 0 to whatever time I'm looking at. And I have natural log of I final over I initial. I've run out of space on this page, so I guess I'll go to the next page on that. I'll put I final. Can't remember. Oh, it was R over L, right?
Yeah.
Yeah. So that gives me natural log of I final over I initial equals minus R over L T final. And so get rid of the natural log by using the exponential, the inverse function, and I will have IF over I initial is equal to E raised to the minus R over L T final. So I final is equal to I initial, E to the minus T final over tau, where tau is equal to L over R. And that's what I would get for my solution there. Now that's simpler than what we see in the overall solution, because the overall solution allows for different possibilities. You know, the overall solution has I at any time is equal to I initial minus I after infinite amount of time. Well, this answer here presuppose I infinity is going to be 0. You're going to have no current after infinite amount of time. Actually, for this circuit, you're not going to have no current at the infinite amount of time, are you?
That's off.
Did I make a mistake somewhere in dropping something out?
Well, where did the voltage go?
Where did the voltage go?
Did it go to the previous?
If voltage is 0,
Down.
then there wouldn't be any current problem.
Yeah, I took that out because I did the homogeneous solution. The problem, that actually is where the problem is, because you start with some current depending on the initial position of the switch and some current depending on the final position. And the way I drew this, it would have to be going like this, or with an inductor, you can't just break it when it's going, or you have significant problems. So in circuits, you have to do things to make non-bouncing switches, because you open the switch and it's going to have to arc, because you've got to have the charge dissipate somehow. And if you've been in circuits class, you've learned about non-bouncing switches. Yes? No? Well, you have to do something to make sure you don't have a problem opening the switch and having arcing occur.
And the concept for this would be what?
So the concept for this would be that when because this was with an inductor, my concept would be that the voltage induced in an inductor is proportional to the derivative of the current, and the voltage across a resistor is proportional to the current. And so using Kirchhoff's voltage law, I can combine those and solve. So in my problem, I should have been a little more careful with my voltage there and the switch action, instead of just finding the homogeneous solution.
So for us, though, we can do the same thing then, just do the homogeneous.
Well, what we actually have here is the homogeneous solution I did correctly, and the particular solution is going to be with a constant added in. And so I would have I have this here that I can't remove, so that's going to be, it's going to be included with the I, right? I'm going to have to combine the E minus IR is equal to L di dt, and then divide both sides by E minus IR. Did you follow, or did that lose? I'll just do it. So the actual way to do it, I have after switch, it includes constant E. So I have E minus IR equals L di dt. Right? That's the same as the equation that we had here, except for I did the particular, or the homogeneous, and I should have paid attention to the particular. And so then separating variables, there I've separated variables. Now this isn't, I generally would have liked to have taken the R out, but I didn't. So there I have it. So then if I integrate both sides independently here, using the same limits as before, for the right side, I have to be a little more careful. So I'm going to let U equals E minus IR Therefore, wow, that's not therefore. du is equal to minus r di. So di is equal to minus du over r. And so the right side integral becomes integral of minus 1 over r du over u. And so that's going to introduce the natural log of u. Add another page. So when I do this integral, I have excellent. I got 1 over L written before it crapped out. Sorry. Natural. It's so that's what I get when I do that integral. It's not really problematic, but it seems seems harder. So now I'll multiply r across and the minus sign. And I'll go ahead and multiply both sides by r inside of this. So I'll have.
Where did your T go on the left-hand side?
Where did my what go?
The T final?
My mistake. That has to be there or you don't have a solution that's a function of time. Somehow that doesn't feel right. Are my units right in here? The E, I mean, because E is IR, not I over R. And so I think when I put in my limits, where's my U substitution written? Yeah, it was IR, not I over R. Okay, that's now I'm going to divide both sides by R. And then use the exponential. Multiply across. And finally, solve for I final. Switching the order here because of the sign change. Right. Moving the I final over and this over changed the sign. So that's why I changed the order of I0 and E over R. It was just rearranging. And that's the correct, the correct equation. And now you see it is the full-on equation because this here is the I infinity. And so it's I infinity plus I0 minus I infinity, e to the minus t over tau. Question, Aaron?
So, like what we worked out in class when we did this was that we were given a function for I, and it was, I don't know if that's like always the function I equals I max sine omega t, but is that what we would be doing with these? You would be giving us this equation and we'd plug it into the differential equation?
No, for this here, you would be finding this equation.
Okay.
Right, for general physics version, they can't do that. But for calculus based, we can find, so this is the equation for the current as a function of time.
So what was it that we worked out in class last time?
Well, in the calculus based class?
Yeah.
In the calculus based class, we worked this out for an RC the first time.
Mm-hmm. And we also did an R.
And
that was like, I don't know, last week? Yeah, it was last week because we did the impedance.
I didn't think we did an RL circuit last week. I thought we did finding inductance. And
we did recon reactance.
Yeah. But this here is exactly equivalent to what we did with the capacitor, which is why I didn't repeat it, because it's exactly equivalent. But I repeated today in review. Okay, we only have 3 minutes left. We have 3 other options. So we have the integral form of Ampere's law. You are not going to have this intermediate piece. That's just there to identify that the current is the integral of the current density dA. So Ampere's law, the integral over a loop, this is not a physical loop, it's a loop that you're imagining for calculational purposes, just like with Gauss's law, is equal to mu naught times the current enclosed. This is useful to us when we have a nice exploitable symmetry, such as having a long straight wire. If we don't have a symmetry where we can make a loop where on each side either B dot dl is B is constant and the angle between dl and B is constant, or they're perpendicular, then it's not going to be easy for us to use. So we restrict using Ampere's law to situations where we have those easy geometries. And we only saw, as far as I know, there are only 2 easy geometries. One of them is the long straight wire. The other one is the solenoid. Because with the solenoid, you make the infinite box. On the sides, B is perpendicular to dl, so B dot dl is 0. At the top, B is 0, so B dot dl is 0. And then you're just left with the B dot dl on the inside. So you would have, if you have a solenoid and you're looking for the magnetic field inside the solenoid, or if you have a long straight wire, then Ampere's law is going to be the choice. You could also then take, well, because I can find the inside of a solenoid easily enough, I can find the magnetic field outside of the solenoid by knowing what it is on the inside and then choosing a non-infinite length box to find what it is outside. So those are, 2 situations, a solenoid or a straight wire that you would use Ampere's law. If you don't have those and you're asked to find the magnetic field due to current in a wire, then you go to the Biot-Savart law. So just like on the last test where you had a wire like this with charge on it, you could have a wire like that with current. Now, of course, you have to have wires coming to it to bring the current to it. And you can arrange the geometry so those wires don't affect your answer. If you have something like this without the complete symmetry, then you would use the Biot-Savart law. So for instance, if I have a current of I that's going through this loop and I want to find the magnetic field here, then I would say, okay, great. For this location, the radius is constant And the ds cross r is always going to be 90 degrees. So it's just going to be ds times r. And then it becomes a simple integral. Just like last class or last test, it turned out to be a reasonably simple integral. Now, you can also have the hard cases. I'm certainly not going to give you something like this where you have a random shape and a function for it that's a large polynomial and ask you to find it, right? Because that's too complicated. But there are lots of variations of things where the ds cross r is reasonably easy to do. Remember, we did use it for a long straight wire to show that you can also use the Biot-Savart law for a long straight wire. Because I am now on my last minute, the last one was Faraday's law of induction, which has with it, of course, the understanding of Lenz's law. And so in using this, you would have to be able to calculate the flux going through a real surface now, not an imaginary surface, to determine what the EMF is produced. So you would just, find an equation for the flux, and based on your situation, find what that is, and then take the derivative with respect to time. So the cleanest and most common example of this is you have an electric generator that is rotating coil of N turns and area A. So let's go with sine. So if your flux is BA sine omega t, then you just take the derivative of that, and you'd have,
Wouldn't it be NBA sine omega t?
because my equation here had the n,
Oh, right.
you have to pay attention to that because sometimes you see it without the n, and you're including n in the flux. Sometimes you see it with the n, you don't also include the n in the flux then. Derivative of sine omega t is omega cosine omega t. And that would be the EMF induced. Another common example is I have a loop of radius r in a region with magnetic field B, and you have either B is a function of time, so the magnetic field is changing, or r is a function of time, so the radius is changing. You're going to have a growing or shrinking loop. It doesn't matter if you have both of them changing or just one. You find the flux, right? You would have the flux is B pi r squared, and then take the derivative of that with respect to time to find the induced EMF in the coil. Or in the loop. I now have finished my planned review. You can question away, or you can walk away. Aaron.
What's the sine omega t in the b dot dA equals BA sine
This right here?
Yeah.
That's calculating the flux.
Okay, but how did you get the omega t?
Because I said rotating coil, N turns, and area. Okay. I meant to include here that it was rotating with, in my brain I said it, but obviously I didn't. Rotating coil with angular frequency omega. In my brain it was said, but clearly it wasn't said.
So it's for a magnetic field like magnetic field's going this way. It's for a coil that's rotating like this.
Yeah, it's the basic picture that we saw. So it's rotating with angular frequency omega, and it has some area A based on the dimensions of the loop here.
Because sine, cosine doesn't matter because it's just 90 degrees.
Yeah, it does. What it would change is if you have a cosine or a sine here, and if you have a plus or a minus here. But you'll have fundamentally the same answer, and it's just your starting time that changes if you change from sine to cosine. Or changing the plus and the minus sign. It's only changing your starting time. It's not changing the actual variation with time. Any other questions about anything for the test?
On one of your calculus-based problems, on the practice test where you had two semicircles, one wire was had a smaller radius than the other wire, but then you were looking at a point in the center between those two semicircles.
Let me look at the problem
Yeah.
for it.
Seems like half a watermelon or something.
Okay. So this was a problem like what I just showed a second ago, but with a little more complication. You have two semicircles that are connected like this. So you have current that is going like this, and it gives you R1 and R2, and then it asks you to find the magnetic field at the center. And then it gives us a bunch of numbers, but numbers aren't important until the very end. So starting off, how many pieces of wire do you have? I mean, how many segments? How many distinct segments for calculational purposes? 4, okay? So we're going to look at each one of those 4 and consider what it will contribute. So before I even go into that, I should have said, which law is going to be the one I should use here? Why not? Or why?
Because it's not a long straight wire.
Okay. Because no easy symmetry is my answer. The two easy symmetries would be the long straight wire or the solenoid. Okay, so I'm going to use the Biot-Savart Law. And now for each one of those, so let me just label these as segments 1, 3, 4, 2. So radius 2 goes with segment 2, radius 1 goes with segment 1, 3 and 4 are the other two side. So if we look at these, for the wire at radius 1, yeah, is it going to make a magnetic field at position A? And if so, what direction?
Yes.
Okay, I have an answer of yes and coming out. Right, you can actually use, if it was complete circle, wrap your fingers direction of current, your thumb points out. That's direction to be at the center. If it's a complete circle, half a circle should just do half of what the complete circle would do. I could actually say, aha, it's half of a complete circle, then thus I should have half of what I'd have for a complete circle, and I could do it short without using calculus, but you had to use calculus in this. Okay, what about section 2? It's going to be going in, right. What about section 3? It's not going to make a magnetic field there because the magnetic field from 3 is going to be always doing loops like this. It's not going to have anything on the axis of that wire, no matter where you are. And what about section 4? No. So we established that sections 3 and 4 cannot create magnetic field at A because A is parallel to, well, on axis parallel to right? There is going to be magnetic fields like here due to 3, or magnetic field here due to 3, but not on the axis because it's doing circular loops. So then I use the Biot-Savart Law for sections 1 and 2. So for B1 due to section 1, I have B1 is equal to, and what was the equation? Mu watt over 4 pi I ds cross, and I'm going to put r hat over r squared, right? So that's equal to mu watt I over 4 pi ds cross r hat is just going to be ds because r hat is always perpendicular to ds if you're going in a circle and using the radius in the arc. And r is constant at r1. And so then I just have to integrate this from 0 to pi r1. Right. Yes, because the length of half a circle is 1/2 of 2 pi r, or pi r, and that was r1. And so if I multiply that through, that's going to give me mu watt I pi r1 over 4 pi r1 squared. Cancel one of the r1s, cancel the pi's. I have that. And then I do for the B2, and what do I get for B2? Yeah, you don't have to do it again. It's just going to be over R2, right? It's all exactly the same. So, and remember, there was direction to this, and the direction to this was for R1, it was coming out. That's not how you spell out. For B2, it's going to be mu watt I over 4R2 going in. And so what's the total magnetic field? And then you have to put in your numbers. I trust that agrees with the answer I wrote there.
Yeah, thanks. Yeah.
All right. Anything else? Nate.
How do you know if the direction is going out?
Okay, that's what we established at the beginning. You told me for R2, for that arc, that it was going in. Remember? Using the right-hand rule, you went like this for R2, and so that's why I put the in direction with it. And for the R1, it's coming out.
Yeah.